Okay. This tutorial, as soon as this monstrosity passes, this tutorial will deal with the dot product of vectors. And its applications, of course. Okay. The dot product is also referred to as the scalar product. As the word suggests, as the word product is suggesting, you're multiplying two vectors using the dot product rule. So here are two vectors. Let's say this is vector A and this is vector B. And theta is defined as the angle subtended by A and B. By definition, A dot B, that is the dot product of A and B, can be defined as the modulus of A times the modulus of B times cos theta, where theta is the angle subtended by the vectors A and B. You will remember there is a special way we defined the angle subtended by two vectors. Now notice, on the right hand side, modulus of A, modulus of B, cos theta. The result of multiplying one vector A by another vector B gives you a result that is a scalar. Modulus of A is a scalar, modulus of B is a scalar. Cos theta is also a scalar. So that's one reason why they refer to it as the scalar product as well. You're taking a vector, multiplying it by another vector, and getting a result that is a scalar. Okay. Now, as you've seen before, the definition of the dot product rather can be used to prove that two vectors are perpendicular. If two vectors, let's say A and B, I'm losing it here. If vector A and vector B were perpendicular to each other, then that would mean the angle subtended, the angle between them would be 90 degrees. That would mean that theta is 90 degrees. If you plug that into the formula, you end up with A dot B is the modulus of A times the modulus of B, cos of 0. Cos of 90, what am I saying? Cos of 90. Cos of 90 is 0, and that would make A dot B go to 0. So if you want to prove that two vectors are perpendicular, you simply prove that the dot product is 0. Or if you know that the dot product of two vectors gives you 0, then you can conclude that the vectors are perpendicular to each other. So here's the conclusion from that. Summarized. If A dot B gives me 0, it implies that A and B are perpendicular, and vice versa. If A and B are perpendicular, then A dot B gives me 0. Okay. Now the dot product, especially in 3 dimensions in which we were working, the dot product is more often used not so much to find A dot B, it's mostly used to find the angle between the 2 vectors. There's actually another way you can actually find the dot product. If the vectors A and B are given in either Cartesian vector notation or column vector notation. And then you use the fact that you now know the dot product to find the angle between the 2 vectors. Let's go through that process. Finding A dot B. Let the vector A be given as A1I plus A2J plus A3K. And we're going to let the vector B be equal to B1I plus B2J plus B3K. If I'm going to find A dot B, then the dot simply means multiplication. So I'll simply put the 2 vectors side by side, A1I plus A2J plus A3K. I'll put them side by side and multiply them. Dot B1I plus B2J plus B3K. And the objective of multiplying, okay, what's happening here? We simply multiply each term in the first bracket by each term in the second bracket. A dot B can be written as A1 times B1 times I dot I plus A1 B2 times I dot J plus A1 B3. Oops. A1 B3 times I dot K. Then the second term in the first bracket by all the terms in the second bracket will give me A2 B1 times J dot I plus A2 B2 A2 B2 times J dot J plus A2 B3 times J dot K. And then the last term in the first bracket by all the terms in the second bracket will give me A3K, A3 B1 times, oh boy, still trying to get accustomed to using this stupid machine. A1 B3, sorry, A3 B1 times K dot I plus A3 B2 times K dot J plus A3 B3 times K dot K. Now, if you think about it, what do we know about the unit vectors I, J, and K? They're mutually perpendicular to each other. Unit vector I is parallel to the x-axis, unit vector J is parallel to the y-axis, unit vector K is parallel to the z-axis, and they're all mutually perpendicular to each other. We just learned that when vectors are perpendicular to each other, the dot product is 0. Even if they are unit vectors, when you dot them, the dot product would be 0. So 6 of these terms will go to 0. let's see, these two will go to 0. These two will go to 0. And these two will go to 0. Now how about if you dot I with itself, or J with itself, or K with itself? Well, you get 1. If you think about it again, I dot I is equal to the modulus of I. Well, I is a unit vector, so its magnitude or modulus is 1. Then the modulus of the same I times cos of the angle between I and I. The angle between the unit vector I and the another unit vector I is 0. Everybody knows cos of 0 is 1. 1 times 1 times 1 gives me 1. Similarly, J dot J and K dot K will also give me 1. What's the moral of this story? If you look at the end result of the dot product, A dot B will leave me with this term here, A1B1, where the I dot I gave me 1. It will leave me with this term here, plus A2B2, A2B2. J dot J gives 1, J dot J gives 1. And it would also leave me with this term here, A3, B3. K dot K would give me 1. And if you look back at where we had the two vectors side by side, I'll write it back. A dot B, which would have been A1I plus A2J plus A3K dot B1I plus B2J plus B3K. All you're doing, the end result is the coefficient of I times the coefficient of I, the coefficient of J times the coefficient of J, and the coefficient of K times the coefficient of K. A1B1 plus A2B2 plus A3B3. I just went through that proof to make you appreciate where this result comes from. You don't need to prove it every time you need it. You just use it to your advantage. Okay. And by the way, if the vectors were given in column vector form, let's say A was given as A1, A2, A3, and B was given as B1, B2, B3, then A dot B would be equal to A1, A2, A3 dot B1, B2, B3. And if you look at the end result, all you did was to multiply across these terms. So the result here is the same, whether they're given in column or Cartesian form. A1B1 plus A2B2 plus A3B3. And now that we know how to find the dot product, let's use it to find the angle between two vectors. All right, let me find a nice example. Given that vector A is equal to I minus j plus k, and vector b is equal to 2i plus j plus 3k find the angle subtended by A and B. Okay, so we will invoke the dot product. A dot B is equal to the modulus of A times the modulus of B times cos theta. So we put the two vectors side by side on the left hand side. I minus j plus k dotted with 2i plus j plus 3k. That must be equal to the modulus of the first one. Well, remember how you find the modulus of a three-dimensional vector? It's the square root of the square of the I, j, and k coefficients. So that would be the square root of 1 squared plus a negative 1 squared plus 1 squared times the square root of 2 squared plus 1 squared plus 3 squared times cos theta. If we dot on the left, remember how we do that? You multiply the coefficients. The results are above there. It's 1 times 2 plus a negative 1 times 1 plus 1 times 3. And that must be equal to, on this side, that looks like a root 3. The next one looks like a 9, 10, root 14, it looks like, times cos theta. On the left, I have 2 and 3, 5 minus 1 is 4, is equal to root of 14 times 3. Yes. Times cos theta, which makes cos theta is equal to 14 3s is what, 42? 3 4 is 12, 3 1 is 3 and 1 4. Yeah, 42. So therefore cos theta is equal to 4 upon the square root of 42. And theta would be cos inverse, or whatever that number is, for root of 42. Okay, you can figure that out for yourself. So that's one way you can utilize the dot product. I'll show you another example. Let's say you were given the 3 vertices of a triangle. You're given the coordinates in 3 dimensions. So let's say the point A had coordinates 1, 1, 2. The point B had coordinates 6, minus 2, and 3. And the point C had coordinates 2, 0, 5. So what we're going to do, we're going to draw that triangle. Typical question would be to find the vectors, find the displacement vectors AB and AC. That's part A. Part B, hence, find the angle subtended at A. And I'll call that angle theta. So the first thing we need to do, I'll use column vector notation for this one. In this case, you need to write down, first of all, the position vectors of all the points. And by definition, you will remember the position vector of a point. The position vector of a point is the vector that joins the origin to that point. So the position vector of A would be OA, and that will be given as, in column vector notation, 1, 1, 2. Position vector of B, OB, that would be 6, minus 2, 3. And the position vector of C, OC, will be equal to 2, 0, 5. So now I need to find the displacement vectors AB and AC. AB has to be OB minus OA. Position vector of the B minus the position vector of the A. So that would be 6 minus 2, 3, minus 1, 1, 2. If you take the difference, I think I can subtract. 6 minus 1, that gives me a 5, minus 3, and 1. Double check. 6 minus 1 is 5, minus 2 minus 1 is minus 3, 3 minus 2 is 1. So in column vector form, that's the vector AB, the displacement vector AB. The displacement vector AC is given by OC minus OA. That would be given by OC 205 minus OA, which is 112. Taking the difference, you end up with 1 minus 1, 3, it looks like. 2 minus 1 is 1 minus 1, 5 minus 2 is 3. Good. So if I wanted to find the vector subtended at A, the vector theta shown up in the diagram, then I obviously need to find the dot product of the two vectors that subtend that angle. So I'm going to dot the vectors AB and AC. Using the definition, AB dot AC is equal to the modulus of AB times the modulus of AC times cos theta. Okay, I'm going to take this up to a certain point and you're going to finish it. AB dot AC, that would be 5 minus 3, 1 dot AB dot 1 minus 1, 3. And that must be equal to the modulus of AB, which would be the square root of 5 squared plus or minus 3 squared plus 1 squared times the modulus of AC, square root of 1 squared plus or minus 1 squared plus 3 squared times cos theta. On the left, we're going to have, what's this, 5 plus 3 plus 3, I think. And on the right, I'll have 25, 9 and 1, 10, square root 35, times the square root of 11, it looks like, 3 and 1, 4 and 1, no, 3 squared is 9, 11, I can't add these days, cos theta. And you guys can probably take it from here and make cos theta the subject, and then cos inverse. All right. There are going to be other cases in which the dot product appears, but I think this should explain satisfactorily how to perform the dot product, whether the vectors are given in Cartesian notation or column vector notation.